All right, there we go. All right. So then let me make this large again. All right, so then just really quick, just like I just said, if our quartiles are Q1, Q2, and Q3, just like we did for the range, we found the largest value and we subtracted the smallest value from it. So too are we going to find the interquartile range by taking the largest quartile and subtracting the smallest quartile from it. So that's then going to give us the range in between our quartiles. All right, so let's try to do those things that we learned last class and also including the interquartile range for this first example right here. It's asking us to calculate out the 5-number summary, the interquartile range, and the percentile rank of the number 5. So, which one do you guys want to do first? Let's do the 5-number summary first. Cool. Do the 5-number summary first. All right, in the 5-number summary, we're looking to have 5 numbers in it. And what are those 5 numbers that we're looking for? Awesome. So of these 5 numbers, which one is going to be like the easiest to find? The min and the max, right? So in here, what is the minimum value? And what's the maximum value? Everybody good so far with those 2 numbers? Now we just need to find Q1, Q2, and Q3. Whenever we were talking about how to find Q1, Q2, and Q3, especially if you guys remember that race that I talked about, which was the first one that we found? Was it Q1 or Q2 or Q3? Q2, right? So Q2 is the same thing as what? The median of the data set. So whenever we're trying to find the median of the data set, what's our necessary first step? Put everything in order. Cool. So let's put everything in order. So if we put everything in order, then from smallest to largest, we're going to have the numbers 2, 3, 3, 5, 6, 6, 8, 9, 10, and 11. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. Awesome. Got them all. All right, so whenever we're trying to find the median of a data set, the first thing that we have to do is put in numerical order from smallest to largest. We just did that. Now what's the next thing that we have to notice?
Even or odd.
Do we have even or odd, right? How many values do we have here? Do we have even or odd? Even. You have 10, so we have an even number. So therefore we know that the median of this data set is going to be what? The average of the 2 middle numbers, right? So the 2 middle numbers happen to be this number 6 and this number 6. So therefore the median of the data set is going to be 6. So therefore we can put that in our 5-number summary as what? Q2, 6. All right. So the really, really, really important thing to realize here is this, right? And this is a very, very, very common mistake. The median of this data set is not this number 6. And the median of the data set is not this number 6. The median of the data set is literally right in between these 2 values, right? That's why we're finding the average of those 2 values. So the median of the data set you can think of as like this point right here. That's the median of the data set. Right? Is everybody good with that? That's what we did then. We found 6 plus 6 and we divided by 2 to find the middle of these 2 points. And that's this spot right here. Now, it just so happened that it also turned out to be 6, that this dot right here also happened to be 6. So that's why we recorded 6 right here. If this number right here wasn't a 6, if this number right here was a 7, then I think everybody will still agree that the median of our data set is going to be in between these 2 numbers, the average of those 2 numbers. So then this would just become 6 plus 7 divided by 2, and then our number up here would have just been 6.5. Right? Is everybody good with that? So therefore, the important thing about this is this. the median of our data set does not have to be in our data set, right? 6.5 is not in this data set, right? Is everybody good with it? But it's still nevertheless the median of the data set. So whenever we have an even number of values, it's completely possible to have a median that's not in our data set. We're just going to pick whatever is in between these two numbers right here, right? Is everybody good with it? Now, same thing is, now let me backtrack and erase this stuff. Same thing is true if these two numbers are still 6. Just because now they're both 6s doesn't matter. We're still going to find what's in between these two. It just so happens that what's in between these two is the same number as this. But the important thing here to realize is that the median, in this case, is not a part of this data set. It's technically what's in between these two. That's why I'm saying it's this dot. Right? Is everybody good with that? Whenever we have an even number of values, this dot right here, this becomes our median. But now the important portion about this is that this right here, from this 6 down, becomes our lower set. And from this 6 up, this becomes our upper set. Right, is everybody good with this? So now, if from this dot, not including the dot down, and from this dot, not including the dot up, this is our lower set and this is our upper set. Then if we wanted to find Q1, how do we go about finding Q1? Find the median of the lower set, and that number is 3. And then if we wanted to find Q3, how do we go about doing that? Median of the upper set, and then it's 9. Awesome. Everybody good with 2, 3, 6, 9, and 11? All right. So here, the median does not have to be a part of our data set. And whenever we include this number right here as Q2, it's not going to be included in our lower set, and it's not going to be included in our upper set, right? So we're not including this dot in the lower set, and we're not including this dot in the upper set. All right. I know I'm stressing that a lot. It's going to be even more so important in the next example, so I wanted to make sure that that I highlighted that back sufficiently. Either way, we just finished up the question.
Just to clarify real quick, if you have an odd number set with the lower and upper set both be even numbered sizes, you just leave out the middle value?
Great question. That's not quite right, and we're going to see why that's not quite right when we do the next example. Because if we start off with an odd number of values, right? Let me just say that here, let's just say that 6.5, that wouldn't work out. Let's say that we had an odd number of values. So I'm going to change this number to a 7, and this number I'm going to say, I'm going to squeeze in an extra 6 there, right? Now we don't have 10 values, we have 11 values. Now whenever we identify Q2, what would Q2 be in this case?
Q2 would be
6. This 6 right here, right? So now we're not going to include this 6 in the lower set or the upper set. But now how many values are in our lower set? It's 5, right? It's not an even number, right? Great question. Great question. So let me change this stuff back. But yeah, we're going to have that down here because down here we have odd numbers. So we're going to practice that again. Great question. Everybody good with how to do a 5-number summary? Any questions about 5-number summary? All right. Then the next thing that it's asking us to do, let's just go down the list. The next thing that it's asking us to do is the interquartile range. Interquartile range is what we're abbreviating as IQR. Whenever we want to find the interquartile range, what's our formula? Q3 minus Q1, right? It's already up there. Q3 minus Q1. Here, Q3, I think everybody will agree, is equal to 9. Minus Q1, which is equal to 3. So therefore, our interquartile range is equal to 6. Piece of cake, right? Hopefully the first exam is nothing but IQRs. You guys nail it? Yeah, question?
Wait, so when you're finding Q1 and Q3, it's always going to be like an odd number on the upper and lower sets?
That's right. Yep. Say again?
That's a good way to know if you got the right answer.
Yeah, exactly, right? Like you can see if you're messing something up, it's like an in-between like check. Awesome. questions about IQR? Then the percentile rank of the number 5. So the percentile rank of 5. All right, if we're trying to find the percentile rank of 5, remember that whenever we're finding the percentile rank, it's just kind of like getting rid of the superscript, whatever we just found, right? Like we went over the example earlier, the 60th percentile rank would just be 60. So we're trying to find the percentile rank of 5. What do we have to find first? Right? Remember that if we knew it was the 60th percentile, we would just get rid of the th, and that becomes our percentile rank. So if we're trying to figure out our percentile rank, we first have to figure out the percentile. Cool. First have to figure out the percentile. So first have to figure out the percentile of 5. Whenever we want to figure out the percentile of 5, what are we looking for? First, we're going to do how many values are equal to or less than 5. And then we're going to take how many values we have like that and divide it by the total number of values that we have, right? We're trying to find the percentage of values that are equal to or less than the number 5. All right. So how many values in our data set are equal to or less than 5? 4. 1, 2, 3, 4. Right? Is everybody good with that? How many total values do we have in our data set? 10. So therefore, the percentile of the number 5 is the 40th percentile. 40% or just the 40th percentile. Right, is everybody good with that? All right, well, if 5 is the 40th percentile, then what is the percentile rank of the number 5? Cool, so this is just 40. Everybody good with the percentile rank of the number 5 being 4? D. Any questions then about this first example? All right, then take maybe 2 or 3 minutes or 4 minutes or so for yourself and see if you can do this next example right here by yourself. Get until the IQR, interquartile range. And after the interquartile range, there's a little quirk to this problem. So then we'll do it after that together. So just do 5-number summary and the interquartile range. Does anybody need a little extra time? All right, then let's start doing this one together. So if we're going to do the 5-number summary, again, we're trying to find X min, Q1, Q2, Q3, and X max. Here, the two easiest ones to find are the minimum value, which is 0, and the maximum value here, which is 10 for X min and X max. Then the next thing that we want to do whenever we want to find these different quartiles is they're all essentially medians of something, so we have to put these in numerical order. If we put them in numerical order, we get 0, 0, 1, 2, 3, 3, 5, 7, 7, 7, and 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values. All right, so just like we did before, the first one that we're going to find is going to be Q2, which is the median of the entire data set. We put it in numerical order, so then the next thing we have to realize is whether or not we have an even or an odd number of data values. We have an odd number of data values, making the middle value equal to our median of the data set, or equal to Q2. So I can put 3 right there. Now, just like we had in the previous example, the median is not going to be part of the lower set or the upper set, right? Which is exactly what we did in the previous example. So the median is not part of the lower set or of the upper set. So then if we wanted to find the median of the lower set, that's going to be the number 1, since it's going to be an odd number of values, and that's going to be the middle value. And then the median of the upper set is going to be this number 7 right here, which gives us this as our 5-number summary. Everybody good with this being our 5-number summary? All right. Then the next thing that we want to do is the interquartile range, or IQR. Our interquartile range is defined as Q3 minus Q1. Well, Q3 we already determined is 7 minus Q1, which is 1. So therefore, our interquartile range is going to be equal to 6. Everybody good with IQR being equal to 6? All right. So the next thing that we want to find then here in this problem is find the percentile rank of the number 4. Well, just like we did before, whenever we're trying to find the percentile rank of a number, we first are going to find the percentile of that number, and then we're going to get rid of that superscript. So whenever we're trying to find the percentile of 4, we're going to try to identify how many values we have that are less than or equal to the number 4, and then we're going to divide that by our total number of values. So another way of saying that is we're going to find out what proportion of our values are less than or equal to the number 4. Well, here we have 1, 2, 3, 4, 5, 6 values that are less than the number 4. So we're going to have 6. Out of the total number of values that we have, we already said that we had 11 of those. So 6/11 is equal to 54.5%. Well, here's where that little quirk comes in that I talked about, right? We don't have an even percentage. So technically what we have here now is the 54.5th percentile. Well, we don't really record percentiles in fractions of a percentile, right? Like, we don't have any decimal places right here. We always want to keep it as whole numbers. So now the question is, well, is this the 54th percentile then, or is this the 55th percentile, right? Well, let's think about this here. Well, let me ask you guys this first. What do you guys think? Is that the 54th percentile or the 55th percentile?
4.
Hear people saying 54. Anybody think it's the 55th? Cool. So why do you think it's the 54th percentile?
Because the other half of 54 to get to 55 isn't included. So when you want to just include what's included?
Yeah, exactly, right? So think about it like this. What we're looking for is the percentage of values that are equal to or less than something, right? Now, what we just found out is that 54.5% of values are equal to or less than that, right? It might not be really, really obvious since we're just working with 11 numbers, but let's say we're not working with 11 numbers. Let's say we're working with 11 million numbers, right? Now, if we're working with 11 million numbers, and I say, hey, some value that I just picked out is greater than or equal to 54.5%. If I say, well, let me just call it 55%. Well, now what I just did is I just took that 0.5% times 11 million numbers, and I said that all those other numbers are also less than or equal to the value that I just picked out. And technically, that's not right, right? So 0.5% of like 11 million numbers, I don't know how many that is, like 500,000 numbers, but those 500,000 numbers that I then included extra, like that would be an incorrect statement, right? So therefore, whenever we end up with a number like this, and we only want to have it as a whole number, we always, 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 always round down, right? Always round down. Regardless if this would have been 54.99% or 54.2%, whatever the decimal place is, you always, always, always round down. So you always round down. So therefore, this is going to be the 54th percentile. Well, if this is the 54th percentile, what's our percentile rank? 54. So everybody good with this example? Any questions whatsoever about this example? How do you guys feel then about interquartile range, 5-number summary, and percentile range? Everybody's good with this stuff? All right. Then let's move on to the next page of notes. All right. I cannot stress how important z-values are. Z-values or z-scores, those two terms are synonymous, is extremely, extremely, extremely important. Not just for this class, but really in all of statistics. Z-values or z-scores are used so much. Now, who of you are first-year college students? Cool. So here's the thing, right? This is one of the things that I didn't realize whenever I was first starting college is, like whenever I was in high school, like you can study for like 30 minutes and still be decent and the same, right? But once you got to college, like things tend to not be quite that easy anymore. So one of the things that I didn't realize is whenever I was trying to prepare for a test, what should I prepare whenever I'm studying for a test? And there's little clues that professors always send to students to show what kind of stuff they're going to include on the test and what kind of stuff is going to be heavily emphasized on the test. A lot of times whenever a professor says, oh, this is significant or this is important or we're going to use this a lot, chances are it's going to be on the test and you're going to see it on the test quite a bit, right? Especially if that professor knows anything about teaching. So I'm not trying to hide the fact that this right here is going to be a huge portion of your guys' test, right? And not only on this exam, but this is something that we're going to carry on throughout the semester. So this is something that you have to make sure that you understand. So while I'm going through any of this, if something doesn't make sense to you, ask a question. One of the things that you definitely should not do is you shouldn't say, I'll just YouTube it later. That didn't make sense, but I'll figure it out later. Like, don't do that. Like, you're paying me to teach you, so if you have a question, just ask me that question, and I'll make sure I tell you. Answer your question. All right. So z-scores or z-values are extremely, extremely, extremely important. Right now what we have is we have two formulas to calculate out z-scores. This one right here includes x bar and s. So this is our z formula for what? These are for sample. This one is for sample. And over here we have mu and sigma in it, so therefore this over here is a population, for populations. what we're going to see throughout the semester is, I'm just going to pick on this population one here for a second. What we're going to see throughout the semester is we can always boil stuff down, back down to this formula right here. So as we go on, especially in chapter 4 and chapter 5 and chapter 6 and so on, we're going to start to manipulate this formula a little bit. But once we get to those chapters, we're going to see that the Z formulas that we use in those chapters are just really, really similar to this formula right here. So I don't really require you guys to memorize a whole lot at all in this class. Especially, like I said, you can store stuff in your calculator if you want. However, if there's going to be one thing that you should memorize this semester, it's this formula right here. Right? If you memorize this formula right here, this tiny little formula right here, it's going to make your life so much easier for the rest of the semester. So much so that I say, hey, if tonight or if this afternoon or whatever you go home and you start studying statistics, spend a whole lot of time on this formula so that if you wake up in the middle of the night having dreams about statistics, you're dreaming about this formula right here, right? You guys ever spend so much time during the day that you like started dreaming about stuff at night? Yeah, this should be this formula right here, right? Hopefully it's like something like a positive dream, like like you're eating candy or something like that, and it's not a nightmare. But regardless, whether you're being chased by this formula or you're just hanging out with this formula, it should be this formula that you're dreaming of, right? All right. I hope I've emphasized that enough. All right, so let's see what this formula is all about. The z-score of an observation x is a number z given by these formulas according to whether the data is a sample or a parameter. And the z-score is a measurement of x. Measurement x is the distance of x from the mean in units of a standard deviation. All right. Now, what the heck does that mean, right? So, let me ask you this. Let's say that you saw me playing soccer. And this is me, and I have shin guards on, and I'm playing soccer. And that's a soccer ball, right? And now, let's not put the soccer ball that close to me. Let's just say that the soccer ball is over here instead. And let's say that this soccer ball is 9 feet away from me, right? If this soccer ball is 9 feet away from me, how many yards is it away from me? 3, right? So there's 3 feet in a yard. So then, therefore, this is going to be 3 yards away from me, right? Is everybody good that this right here is then going to be the same thing as 3 yards away? All right. Well, what you just did here by converting feet to yards is exactly what this formula is doing up here, right? Again, remember that our standard deviation, right, what's the easiest way to wrap your head around what a standard deviation is? It's a measure of distance, right? So all that we're doing here is we're expressing it in different measurements of distance, right? So that's what it's doing right here. All right, so let's take a look at this z-value formula. In the numerator, we have x minus mu. If we try to think back on to addition, right, like especially whenever you first started learning about addition and subtraction, what really does subtraction show to you? Right? If you think back to like elementary school or wherever you first started learning about subtraction, and you said, and your teacher was teaching you about subtraction, how did you first learn about what is subtraction? What does it even represent? It's adding a negative number. But if you say, hey, 5 minus 3 is 2. And what does that mean? What does that 2 mean?
The difference.
It's the difference. But more specifically, it's the distance. That 5 is 3 away from 2. Right? That's how you first started learning about subtraction in elementary school. And then, like, chances are, like, there were, like, little magnets, and, like, your teacher would, like, move the magnets back and forth, right? Be like, 1, 2, it's 2 away, blah, 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 right? So you get a visual of it. That's why most of us are visual learners. But anyways, I digress. So all that we're saying right here in this numerator is that we're trying to find out how far apart is x from mu. And again, what does mu represent? The average, the mean, right? So all we're trying to do right here is say, hey, how far away is an x in our data set away from the average, right? Is everybody good with that so far? But now I don't want to just know how far away x is from the average. I want to know it in terms of standard deviations, right? So basically, that's what we did right here. We said, hey, I know that Mike away from soccer ball is 9 feet, but I don't want to express that in terms of feet. I want to express that in terms of yards. So therefore, we took that 9 feet and we divided it by 3 feet per yard in order to get us to 3 yards, right? So we took this 9, we divided by our measure of distance, which is 3 feet per yard, to get us to yards. That's exactly what we're doing right here. We're saying how far away is x from the mean, but we want to express it in terms of standard deviation, so that's why we're dividing it by standard deviation. Right? Is everybody good with this? Does everybody go with the intuition behind what the z formula is trying to do? You're trying to take two things, find out how far apart they are, and you want to express it in terms of a standard deviation. Right? Is everybody good with that? Now, what we're going to see here, and this is why it's a little bit more abstract, but we can come up with different numbers for a standard deviation, right? Last class we did a couple of examples. One of the examples we found a standard deviation was like 2.7, and the next example we found was like 2.1 or something like that, right? So we can have different numbers for standard deviation. So the best example that I can give for that is, it's not consistent like 3 feet per yard, but imagine it as like a shoe size. Right? You know, I have size 10 shoes. Maybe you have size 11 shoes or size 7 shoes or what have you, right? So if we wanted to say, hey, I don't want to find out how many yards it's apart, but I want to figure out how many of your shoes it's apart, and each one of us is going to come up with a slightly different answer. And that's how you can imagine for our standard deviation. But either way, we're trying to find the distance of x to the average in terms of shoe sizes, or here we're just calling that our standard deviation. All right, is everybody good with what a z value represents? So then, let's go down to this picture. Here what we have is, we have our distribution, and it's really, 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 really important that for this, we use a bell-shaped and symmetric distribution. More specifically, what we're going to be using is we're going to be using a normal distribution. And we're going to end up converting this to a standard normal distribution. But all of that is a little bit beyond what we need right now. What we really are just looking at right now is these axes underneath this graph. And that's this, right? If here's our average, our mean, and we go one standard deviation above our mean, then here it says that we're going to have a z value of 1. Right? Is everybody good with that? If we go from our mean and we go 2 standard deviations above our mean, it says that we're going to have a z value of 2. And so on and so forth. Right? Is everybody good with that? So you can think of a z value as being the number of standard deviations that you're away from the mean. Right? Is everybody good with that? Well, now, if you take that concept that a z value is just how many standard deviations you're away from the mean, well, let's go the opposite direction. What happens if we go from the mean, and instead of going above the mean, now we go below the mean? Now we don't have a z value of 1, we have a z value of -1. If we go from our mean and we go 2 standard deviations below our mean, now we don't have a z-value of 2, we have a z-value of negative 2, and so on and so forth. So the way that you can really remember this is a z-value is how many standard deviations you're away from the mean. If you're above the mean, you're always going to have positive z-values, and if you're below the mean, you're always going to have negative z-values. Right? Everybody good with that? Cool. Any questions about that whatsoever? So if I told you that you had a z-value of negative 2.7, what can you tell me about that? That you're 2.7 standard deviations below the mean. Right? Is everybody good with that? And again, the standard deviation is going to change from problem to problem. So that's why you can kind of think about a standard deviation as being like your shoe size. So if I told you that you were 2.7 standard deviations below the mean, for some of you that might be farther below the mean than for others, right? Just depending on what that problem is, the numbers of that problem. All right, everybody good with this so far? So let's try to calculate out a couple z-values. Let's start off with this example right here. Suppose a sample has a mean of 30 and a standard deviation of 5.5. Find the z-score of 35.5. All right. So are we dealing with a sample here or with a population? Sample. So therefore, we're going to have z is equal to x minus over. Awesome. So we have this right here. What am I going to plug in for x bar? 30. What am I going to plug in for s? And then what am I going to plug in for x? 35.5. Awesome. All right, is everybody good with this? If you do this arithmetic, what do you end up with? 1. Because 35.5 minus 30 is 5.5. Then 5.5 divided by 5.5 is just going to give us 1. Everybody good with this? So you have a z-value of 1. You have a z-value of 1. Say that differently in the context of this problem. Good. That 35.5 is 1 standard deviation above the mean. Right, is everybody good with that? Cool. All right, then let's go on to this one down here at the bottom. Suppose a population has a mean of 43 and a standard deviation of 2.6. Find the z-score of 37.8. So take a minute for yourself, see if you can write this one down, and see if you can come up with the correct z-score.
I'm like just not realizing what the first question is asking. And the z-score of this measurement, of this number. So you're finding the z-score at 35.5. Got it.
Yeah,
That's
exactly.
why you put that as your x value, not as your z. Because it said find the z-score, I put it as my z first. Because
I did the exact same thing, and I was like, this
I got
math
it, it
is
just clicked.
weird.
Yeah, like, so this 35.5. So you can think of each number having like its own z-score, right? So whenever it says, hey, if you have this number right here, find the z-score of that number.
Because that z-score for that number is how
All right, does everybody have an answer for this problem? All right, so now we're going to have z is equal to x minus... let me first write down like the general formula. Which one am I going to use? For population, for sample? Good. Mu for the population over sigma, which is our standard deviation. So we're going to have 43 for the mean. So we're going to plug 43 in for mu. We're going to plug in 2.6 for the standard deviation. And then we're going to find the z-score of 37. So we're going to plug that in for x. And we get this right here. Everybody good with this setup? Then what we're going to get in the numerator is negative 5.2. And negative 5.2 divided by 2.6 is equal to negative 2. So we just calculate out a z-score of negative 2. Say that again differently in the context of this problem.
2 deviations below.
Awesome. 37.8 is 2 standard deviations below the mean. Everybody good with that? Awesome. All right. So let's move on then to this top right-hand example right here. Suppose a sample, so let me write down the z-value formula for a sample, which is x minus x bar over s. Suppose a sample has a mean of 20. What can I plug that in for? X bar. And a standard deviation of 1.8. What do I plug that in for? What value of x would yield a z-score of 2? Awesome, so I'm going to plug 2 in for z, and then I'm going to try to figure out what value of x would give me a z-score of 2. All right, is everybody good with this setup? Any questions about the setup? So then, if we multiply both sides by 1.8, we're going to get 3.6 is equal to x minus 20. If we add 20 to both sides, then we're going to end up with 23.6 is equal to x. So an x value of 23.6 would give us a z-score of 2 as long as the mean is equal to 20 and the standard deviation is equal to 1.8. Any questions about this example? Is this making sense? All right, then take a minute or so for yourself and see if you can do that bottom right-hand side one by yourself. Anybody need a little extra time? All right, so suppose a population, so z is equal to x minus mu over sigma, has a mean of 19 and a standard deviation of 3.4. What value of x would yield a z-score of negative 3? Everybody good with this setup right here? All right, then if we multiply both sides by 3.4, we get negative 10.2 is equal to x minus 19. Adding 19 to both sides, we get 8.8 is equal to x. Any questions whatsoever about this last example? How do you guys feel about the formulas of z-scores? Everybody's good with the overall application for z-scores? Right, and let's move on. to the empirical rule and Chebyshev's theorem. Empirical rule and Chebyshev's theorem. So the first thing that we're going to start off is, with the empirical rule. So here, the empirical rule is really specific. The empirical rule says that we can only use the empirical rule if a data set has an approximate bell-shaped relative frequency histogram. So let's stop there for a minute and let's see what exactly it means for a relative frequency histogram to be approximately bell-shaped. Remember that we said that a relative frequency histogram is a type of distribution, right? Is a distribution, and that's the stuff that we kind of explained with like the whole Connect 4, like dropping chips down the chutes, right? Is everybody good with that? Now, whenever we make this distribution and we're dropping these chips down the chutes, it happens to be approximately bell-shaped. And what does that mean? Approximately bell-shaped means it's going to look exactly like this graph down here, right? Everybody kind of see how like this graph kind of looks like a bell, right? Like here's my awesome Picasso of this bell, right? And then here, that's a pretty sweet looking bell, right? Like that's like worthy of like Christmas time right there, right? All right. So here's the bell-shaped distribution. I hope you guys no? All right. I'm just cracking myself up. That's fine. So here's this bell-shaped distribution, right? We can only use the empirical rule whenever we have a bell-shaped distribution. Now, the important thing about this bell-shaped distribution is this. There's a couple characteristics that are really important for it. This bell-shaped distribution is symmetric, right? So if we have symmetry, whenever we were looking at symmetric distributions before, what was the characteristic that we learned about for symmetric distributions? For symmetric distributions, there's always one math concept that always holds. Awesome. Whenever we have symmetry, or a symmetric distribution, we know that the mean is equal to the median. And that is also true for a bell-shaped and symmetric distribution. At least for the ones that we're going to use for the empirical rule. That the mean is going to be equal to the median. Now, there's another very important concept for the empirical rule for a bell-shaped distribution. And we're also going to say that the mean is equal to the median. We're also going to say that it's equal to the mode. So what does that do for our distribution? Whenever you have, well, let's talk about it. If the mean is equal to the median, and that is equal to the mode, how many modes can we have? We can have one mode. Can we have 0 modes? No? Why not?
If none of the data points fall on the same point, but they're all clumped up together closer to one point, then you could have 0 modes, right?
So, great question. Let's say that, I think what you're saying is this, right? Like we have some data values, and then we have 2 values that are exactly the same. So it's kind of like there's like a flat spot on top, and that flat spot holds for 2 values, right? So then what you're saying here is that here we don't just have 1 mode, but we actually have 2 modes, right?
I'm actually saying something else, but I've realized that it's dumb in my own head, so
Okay.
I'm good.
You're backtracking on it?
Yeah,
Cool.
yeah.
Awesome.
I'm going to redact my statement.
You're going to redact your statement. Awesome. Well, let's try to work through it here just to make sure that everybody's on the same page. If you have 2 modes, So again, if you're remembering this like Connect 4, then 2 slots are going to be the highest peaks. Right? Is everybody good with that? So if you have 2 slots that are the highest peak, then you have 2 modes. But now the problem with that is that if we have 2 modes, then we also have to have 2 means. So if you're calculating out some average of a data set, is there ever a possibility where you can say, hey, I have the numbers 1, 3, 5, 5, 7, 7, and 9, right? So they're 5 and 5 and 7, 7, right? So you have 2 modes. Is there ever a possibility where you can come up with 2 averages to a set of numbers? Impossible, right? So whenever you're calculating out the average of a set of numbers, you can only have 1 average. So therefore, if you're saying that the average is going to be equal to the mode, then by necessity, you can only have 1 mode. Right? Is everybody good with that? And then the same thing, obviously, with the median. If you're going to find the middle value, you can only have 1 middle value. You can't have more than 1 middle value. Right? So therefore, we know that the mean is equal to the median, which is equal to the mode. We know that it has to be symmetric. These 2 things right here talk about symmetry. Mean is equal to the mean, symmetry. And our distribution is only going to have 1 highest spot on it. There's only going to be 1 very, very pinnacle of this distribution. Right, is everybody good with that? Now, is it possible to have another distribution that's not bell-shaped, where the mean is equal to the median, which is equal to the mode? Yeah. Is it possible to have another distribution that is not bell-shaped, so it doesn't look exactly like this, but the mean is equal to the median, which is equal to the mode?
Did you have one that didn't taper down at the sides, like it just goes straight down?
Something like this?
Something more parabolic. But that also, yeah. Yeah.
Something more like this, so it kind of stops and it doesn't like taper off.
Yeah.
So here, do we have just 1 mode? Do we have 1 median? And then obviously we're just going to have 1 average. So yeah, this right here would be a perfect example. Right? Another example of it, well, you guys tell me, is this right here, so I am going to make it taper off. Is this right here, would this one right here also apply? Right? For this one right here, how many modes do we have? We just have 1. We just have 1 highest peak. We have 2 smaller peaks, but that doesn't count. We're looking for the most frequently occurring data value. So here we just have 1 mode. If it's symmetric, then we know that the mean is equal to the median. And that's then going to be equal, as long as this right here is the middle spot, then we're going to have the mean is equal to the mean, which is equal to the mode. Right? So, the important thing to realize here is this. The only time we're allowed to apply the empirical rule is if we have a bell-shaped and symmetric distribution. This thing right here. For this thing right here, it's true that the mean is equal to the median, which is equal to the mode. Right? However, we can also find other graphs, other distributions, where the mean is equal to the median, which is equal to the mode, that are not bell-shaped and symmetric. Right? Is everybody good with that? So, it's important to realize that we can only use the empirical rule for this guy. And for this guy, this characteristic holds. But just relying on this characteristic doesn't mean that we have this guy. If we just are given this characteristic, we can also have something like this right here. Right? Is everybody good with it? That's going to be really, 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 really important to distinguish when we can apply the empirical rule and when we can apply Chebyshev theorem. Right? All right. So the only time we can apply the empirical rule is when we have a bell-shaped and symmetric distribution. If it just says bell-shaped, it's assumed that it's symmetric, right? Like, so if you hear bell-shaped, you can assume that it's symmetric. All right. So, and then we have this huge, long definition right here, which is a lot of words. I wasn't an English major, so I don't like a whole lot of words. So what I'm going to do is I'm going to take this definition, I'm going to break it apart here in this picture. So let's see what this all right here means. What the empirical rule says is this. If you have a bell-shaped and symmetric distribution, then if you go one standard deviation above the mean, and you go one standard deviation below the mean, then between these two cutoffs right here, you're going to have approximately 68% of the data. So again, if you do the whole Connect 4 thing with, how many times in a month you call your mother, like we did, right? I know this is not going to be a very nice picture, but I think you guys get the gist. So here I'm making all the dots of, plotting the whole Connect 4 stuff. Then the empirical rule says if you go one standard deviation above the mean and one standard deviation below the mean, then approximately 68% of the dots are going to be in between these two cutoffs. Good? The empirical rule continues and it says if you go 2 standard deviations above the mean and you go 2 standard deviations below the mean, then in between those two cutoffs you get 95% of the data or the dots. And the same thing is if you go 3 above and 3 below, you're going to have approximately 99.7% of the data, right? 3 standard deviations above and 3 standard deviations below. Everybody good with that? Everybody good with what the empirical rule says? Now, we can actually take a little bit more away from the empirical rule. And first off, before I continue, let me say this. It's extremely important that you remember 99.7, 95, and 68, right? So if you go 1, it's 68, 95, 99.7. So for the rest of Chapter 2, but also once we get into Chapter 5 and so on, I'm going to ask you guys again about the empirical rule. And later on in the semester, particularly when we cover Chapter 5, I'm going to say, hey, there's 3 numbers that are really, really, really important that come to the empirical rule. What are those numbers? And you should be able to tell me 68, 95, and 99.7. Right, is everybody good with that? So definitely remember these numbers. They're not included on your formula sheet. Again, I don't care if you're storing them in your calculator, but they're 3 numbers, and these are 3 numbers that are pretty fundamental to statistics. So you should try to remember 68, 95, 99.7%. All right. The empirical rule, we can take a little bit more away from the empirical rule than just 68, 95, 99.7. And one of the things that we can say is this. Suppose I didn't want to figure out how much is in between these two cutoffs. Maybe I didn't want to find out 68%. But maybe I'm going to go to the mean and I'm going to cut this in half. What if I just try to figure out how much is in this region right here? So just in that dark region right here, right? So I want to go to the mean. How much of the distribution is in this dark shaded region? How did you get 34? Divide 68 by 2. You know if it's symmetric, then the left-hand side has to be the same as the right-hand side. If I'm cutting it in the middle, right down the mean, then we know that this sliver over here has to be the same as this sliver over here. So therefore, half is going to be over here, half is going to be over here. So we know that this right here is going to be 34%. And this over here is going to be 34%. All right, is everybody good with that? All right. If I ask you then to figure out what percentage is in this shaded region, so just the new one that I'm making right here, right? Just this one right here. If I ask you to figure out what percentage of the data is in this shaded region right here, take a minute or so for yourself and see if you can figure out what percentage of the data is just in this shaded region. You guys have a number? All right, what do you guys think it is? 13.5. So let's see how you got 13.5. 13.5 is correct. So what we're saying here is this. We're trying to figure out just this one sliver right here. Just that one. Well, what we know is that from this spot right here to this spot all the way over here, we have 95% of the data. Right, so everybody good with that? But we also know that from this spot right here to this spot right here, we have 68% of the data. So if we take all of this 95% and we subtract out the 68%, how much does that leave us with? 27%. So we have then that 95% minus 68% is going to leave us with 27%. Well, what that means is that this section over here and this section over here combined have to be equal to 27%. So therefore, if I'm just looking at this right here, what am I going to do with that 27%? Divided by 2. So then therefore, 27% divided by 2 is 13.5%, and this over here is also 13.5%. Is everybody good with why this sliver over here is just 13.5%? Everybody good with how to get that? All right, then take a minute for yourself and see if you can figure out how much is in this sliver, just this one sliver right here. What you guys get? Everybody good with 2.35?
I have a question.
Yep.
Why are we not rounding them up to like 2 or rounding them down to 2, rounding them down to 13?
So, why are we not rounding? So,
Is it because we need them to be more specific for the 99.7% and 95%?
yeah. So, because we have this level of accuracy right here, right? Once we start dividing these by, like, what's ever left over by 2, we're just going to end up with a fraction, right? Imagine it like this. Like, forget what's happening right here with the empirical move for a second. Let's say that we started off with the number 100, right? And then we want to say, okay, let's say that we divided that in half, and we would end up with 50 and 50. Take that 50 and divide it by half. We're still ending up with a nice number. It's still 25 and 25. But now once we start dividing it by 2, now we're going to end up with 12.5 and 12.5. You wouldn't round that down and say, 50 or 25 divided by 2 is 12, right? You still carry that half along with you. That's exactly what's happening here. So all that we're doing right here is we're just dividing things by 2 in order to end up with something. But once we divide that 2, just because we're dealing with a distribution, we still have to carry those decimal places along with us. Yep. Great question. All right, then just to finish this off, from here on up and from here down, we have what's ever left over. So what percentage do we have right here in this sliver? 0.15.
I also had a question real quick.
Yes.
I don't know that this is going to come up. This is more just out of curiosity. But if you had something like a half a bell curve where like the mode was 0,
Yeah.
could you apply the same percentages to it? Because it would only be like the right half of the bell curve. But would it still be like 68% in the first standard deviation?
So, first off, if you just had half of the Bell distribution, you would still have a mode, right? Because it would just come up to this peak right here, so your mode would be 0, right? So I just want to make sure I heard you right. It's not that we have no mode, it's that we have a mode of 0. Right?
Yeah.
Cool. So we're going to have the mode of 0, but now what you're saying is that can I still cut it in half the way that we're doing a certain percentage on one side and a certain percentage on the other side?
No, not exactly.
Well,
Never mind, answer my own question.
you good? You
Yeah.
sure?
Yeah, yeah.
What we're going to see is that, and I think the direction that your question is going is great, because what we're doing right here with these percentages, 68, 95, 99%, only apply to a bell-shaped and symmetric. So I think where your brain is starting to go is it's starting to say, what happens if it's not bell-shaped and symmetric? Well, whenever it's not bell-shaped and symmetric, we're going to use Chebyshev's theorem, which is this thing right up here. And for that, we're going to be given a different formula, and that we can use to any distribution. So half of a normal distribution and so on and so forth. Yep. Cool. Everybody good with this stuff so far? With these percentages? One of the things that I would highly, highly, highly recommend is remembering how to get these percentages. If you remember how to get these percentages, your life is going to be a lot easier. Now, this is not something that you have to memorize. You don't have to memorize all of these percentages, the 34, 13.5, 2.35, and 0.15. You don't have to remember those, because as long as you remember 68, 95, 99.7, you can get all these other ones. Right? Is everybody good with that? So the ones that you definitely have to remember are 68, 95, and 99.7. But if you remember these other four as well, your life is going to be that much easier. Because as we're going to see on your homework and on your test, we're going to have to find z values, and then we're going to have to start finding percentages. And if you know this graph, like the students that usually tend to do really, really well are the students that as soon as they get the test, on the top right-hand side of their test or whatever, they draw this distribution, they write down these percentages, and then once you have to do like 10 or 15 questions where you need these, you can just keep referring back to that graph, right? So it speeds things up a lot quicker, right? So yeah, let me leave it at that. So remembering these percentages is really important. So let's try to apply this stuff. Let me say one quick thing, and I think you guys would put this together relatively easy anyways, but while I have the opportunity to mention it, let me mention it regardless. This spot right here, let me give myself a little bit of clarity right here. This spot right here, what's the z value of that spot? 1. This has a z value of 1. Why is it a z value of 1? 1 standard deviation above the mean, right? This spot right here has a z value of what? This spot right here has a z value of what? You guys get the gist about where these z values are and stuff? So the empirical rule talks about going 1 standard deviation above the mean and 1 standard deviation below the mean. You have a certain percentage in there. You can reword the empirical rule to say going from a z value of -1 to a z value of +1, you have 68% of your data. Right? Is everybody good with that? So even though the empirical rule doesn't specifically, at least the way that your textbook words it, doesn't specifically address z values, remember that if you're going 1 standard deviation, whatever number of standard deviations you're going both above and below the mean, that's the same thing as saying you're going z values above and below the mean as well. Right? Everybody good with that? All right. Let's go on to... I knew you guys were going to make that connection. I just wanted to say it explicitly before we get on to these. So consider a bell-shaped symmetric distribution with a mean of 2,500 and a standard deviation of 300. Approximately what percentage of the data is between 2,200 and 3,100? All right. We can do this, right? So, first off, what we're trying to do is we're trying to figure out, well, let's start off with this. We definitely know that we have a bell-shaped and symmetric distribution, right? So let's start off with that. We have a bell-shaped and symmetric distribution. Let's try to draw a picture of what we're trying to achieve. And once we can visualize where we're trying to go, chances are we're going to get there just fine. So we have a bell-shaped and symmetric distribution. What is the mean of this distribution? 2,500. So if I wanted to add this to my picture, where would I put it? Right in the middle, right? This number right here is 2,500. And then I have a standard deviation of 300. So I'm just going to write up here that my std.dev is equal to 300, because everybody remembers that that's how I'm going to abbreviate standard deviation. All right. So we have our distribution. It's centered on 2,500. We have a standard deviation of 300. But the question is asking us approximately what percentage of the data is between 2,200 and 3,100. So let's annotate where 2,200 is on our graph. I think everybody will agree that 2,200 is less than 2,500. So I'm going to put it over here. 2,200. And I think everybody will agree that 3,100 is above 2,500. So I'm going to put 3,100 over here. Everybody good with this? And now the question is asking us approximately what percentage of the data is between 2,200 and 3,100. So if I wanted to shade it in, we're looking in between those two values, so we're going to be in that shaded region right there. Everybody good with this? All right. Now that we're here, what do we need to do if we're trying to figure out what percentage of the data is between those two cutoffs? What could help us? If we knew standard deviations, right, which we do in our problem, how can we apply the standard deviation? How does that help us?
Because 2,200 is one standard deviation below 2,500.
All right.
And 3,100 is two standard deviations above.
Okay.
You technically have 68%, and you can take the half of the 95% we took, and then do 68% plus the 13.5%, you get 81.5%.
Awesome. So let's take all of that and go a little slow, right? Because that's exactly right. Here, one of the things that, remind me your name again? Betsy. Here's one of the things that Betsy did. Betsy said, hey, first off, I realize that if our standard deviation is 300, then 2,200 is 300 below 2,500. So 2,200 is just one standard deviation below 2,500, right? The way that we're going to try to say this is this. We're going to say, hey, let's try to find the z value that goes along with 2,200. So I'm going to say z value, and I like writing this as a little subscript right here, so I remember when I'm trying to find the z value. That's just my habit, right? That's not like a math thing. That just helps me keep in mind what I'm trying to do. Now, if I try to find the z value of 2,200, Betsy, if you said that this is one standard deviation below the mean, what should my z value end up being? You're close. -1, right? You're good with -1? Awesome. So what we're going to say here is, first off, do I know if this is a sample or a population? Doesn't say, right? So I could use either formula that I wanted. I'm just going to stick with the population one. I'm going to say this is x minus mu over sigma. You could also use the sample one if you wanted. I like the population one better. And here I know that my average is equal to 2,500. My standard deviation is equal to 300. And I'm trying to find the z-value of 2,200, so I'm going to plug in 2,200 right here. Now 2,200 minus 2,500 is -300, divided by -300. And voila, we have a z-value of -1, right? So just like Betsy correctly said, here we have a z-value of -1. Similarly, if we're trying to find the z-value of 3,100, I'm going to again stick with the formula for the population. We have 3,100 minus 2,500 over 300, and that's going to give us a z-value of 2. Just like you said, we're one standard deviation below here, but we're 2 standard deviations above here. Right, is everybody good with that? Everybody's on the same page so far? Well, then what Betsy said was, she goes, well, then I can use the 68%, right? And what Betsy said then is the 68%, and she said, hey, here this goes all the way up to a z-value of 2, but if I stop at a z-value of 1, then in between here, between one standard deviation below the mean, or a z-value of -1, and one standard deviation above the mean, or a z-value of 1, Betsy goes, I know in between these two cutoffs, I already have 68%. Right, is everybody good with that? But the shaded region didn't stop at a z-value of 1. The shaded region went all the way up to a z-value of 2. So therefore, what percentage of the data is in that additional sliver? Well, 13.5, right? Exactly. If we go back to our previous graph, what we're saying is that we just found out that here we have 68%, but our shaded region didn't stop at a z-value of 1. Our shaded region went all the way up to a z-value of 2, so we also have to include this additional region right here, and that additional region is 13.5%. So therefore, we're not just going to take the 68%, we're going to have 68% plus the 13.5%, which, as Betsy correctly said, is equal to 81.5%. Yes?
On a test, why do you show that word?
No, remember that all the questions on your exam is always going to be exclusively multiple choice. So as long as you circle the correct answer, as long as you're not getting like the answer from like your neighbor or anything like that, I really don't care what you do to get that answer, right? You could also, you could just sit there and flip a coin all test long and just choose whatever the coin said. Or a 5-sided die, since they're all like 5 answer choices. Right? Everybody get the gist? How to do this? All right. Then question 1b is asking us approximately what percentage of the data is above 3100. So take a minute or so for yourself and see if you can answer the question of approximately what percent of the data is above 3100. Everybody have a number? What do you guys think it is? 2.5%? Awesome, right? So what I'm going to do is I'm going to do the same thing like I did in the previous example. I'm still going to find the z-value for 3100, but I think you guys will realize that if I apply the same numbers, 3100 minus 2500, which is the mean, I'm still going to get a z-value of 2. But now whenever I want to have what's above a z-value of 2, here I have my z-value of 2. If I want above what's above a z-value of 2, now if I go to my distribution that we had previously, here then what I'm looking for above a z-value of 2, I'm looking from here on up. And as we previously said, here we had 2.35% of our distribution, and from here up we have 0.15% of our distribution. So as you then correctly said, we're going to have 2.35% plus 0.15%, which is equal to 2.5% of a distribution from there on up. Are you guys starting to see why it's really, really helpful to know these additional percentages? Because for Chapter 2 specifically, we're always going to go whole standard deviations above and below the mean. So you're always going to be able to apply these. How do you guys feel about these first couple of examples applying the empirical? Everybody's good with it? All right. So this is what we're going to do. I didn't quite get as far today as I wanted to get today. So let me first do this.